Feel free to ask questions during my talk. Don't wait until the end because you'll forget what you wanted, and then the slide isn't up, so it makes it a lot more difficult. So just raise your hand, and we can answer the questions as we go along. So I work on the Spitzer Space Telescope, which works in the infrared, and I want to speak a little bit about what infrared light is. Most people have some sense of it, and certainly being engineers and scientists here, I think more than passing familiarity with infrared light. But I want to give a little bit of the history of infrared light, in particular because most people don't know how it was discovered and why I think it was actually one of the most important discoveries in the history of science. And it was made by this astronomer named Sir Frederick William Herschel. He was a prolific astronomer. He and his sister Caroline worked in England. They were German, but they moved to England to work. And they made star catalogs for double stars and nebulae. They discovered comets. And most importantly, what most people would say, in 1781, he was the very first person in the history of history to have discovered another planet. He discovered the planet Uranus. Remember, all the other planets were known to the ancients. We don't know who the person was who noticed that there was a planet up in the sky. But this was the first time using a telescope that he actually found a planet other than Mercury, Venus, Mars, Jupiter, and Saturn. So Uranus was the first one. But I would argue that's not his greatest accomplishment. To some extent, somebody with a telescope at some point would have found that planet. What he did is he did an experiment. He asked a very strange question, and this is where I think really that special insight comes in. And his question was, do the different colors of the rainbow have different temperatures? I think that in and of itself is a very interesting thing to ask, because most people wouldn't even come close to thinking about it. Most scientists had not thought about it. So he said, okay, well, I'll put a thermometer in the different wavelengths to see if they have different temperatures. But also he would have a control that would be outside of the light from the prism that was splitting the light of the sun. And the strange thing that he noticed was that the temperature of the thermometer that was outside of the light changed. So that's the critical thing. So what he noticed then was that there was light falling below the red portion of the spectrum, the infrared. And he published this in a paper, odd date for us, but on April 24th, 1800. Experiments on the refrangibility, which just means, I think, refraction of the invisible rays of the sun. Think about this. All the light that you've ever seen is with your eyes, and now he's publishing a paper in a scientific journal saying, there are invisible rays of the sun. Whoa. That's a joke. But no, he had experimental proof that there was light falling, and we couldn't see that light. And I think that discovery is far more important than Uranus, because that took a leap of logic, a leap of experimentation to be able to do it. So why would we do astronomy in the infrared? Well, infrared light has advantages in the sense that you can certainly see through certain things that you wouldn't be able to see in optical light. This is my colleague, Louisa, and she is basically holding a garbage bag, which you can't really see through in the optical, but you can certainly see her hands through the bag in the infrared. But of course, you can't see her eyes in the infrared, even though because she's wearing glasses. Well, glasses are very good absorbers in infrared light. That's why we use them for greenhouses. Or your car gets warm in the summer because optical light comes in, heats up the interior of the car, or heats up the interior of the greenhouse. Infrared light comes out, tries to leave, but that energy can't leave because the glass traps it. So each wavelength has its own advantage. And here's something else. We have a nice little puppy. It has a nice fur covering it, and we see why it has fur covering it, because the heat that's leaving it, basically anything that has a temperature at all, will emit light. A lot of that light comes out in the infrared. So the dog, the heat that it's losing is losing through infrared light, through its eyes, its mouth. You can see it. It's a healthy dog. It's got a cold nose, not much infrared light coming off of there. So you're actually getting extra information about the dog. And then I can ask a question. Is that water hot or cold? I'm asking, anybody want to answer? You don't know. The picture in and of itself does not have enough information to tell whether it's a hot or cold water that's running. But if you look at it at a different wavelength, it's still a picture. If it's warmer, it's going to give off more infrared light. If it's colder, it's going to give off less infrared light. So fundamentally, a single picture is giving you information which you would not otherwise have if you were looking at a different wavelength. So if you're looking at the wavelengths where things that are warm enough are emitting their light, which is they tend to mostly emit in infrared light, you can basically not only see their temperature, but you can basically set a temperature scale and see how warm they actually are.
Sorry, what
yes?
temperature is considered warm?
Oh, no, any temperature.
Any temperature.
Any temperature. Starting from 0 Kelvin upwards, everything that has a temperature emits light. The warmer you are, the more light you emit, but the shorter wavelength light you emit. And I'll talk a little bit more about it in just a second. So another question, is the hairdryer on or off? Notice that you can't actually see the button there in this my cleverly designed picture. You can't tell again, but if you're looking at it in infrared light, you can certainly see that there's a lot of hot air coming out of the hairdryer. So hopefully I made a good case that looking in the infrared is a good thing to do for astronomy, but then notice between the time of 1800 with Herschel publishing something about the discovery of infrared, there really wasn't much work in infrared astronomy. Why? Well, there are a couple of problems. One is that, as I was saying, anything that's warm emits light, and anything that has the right temperature is going to emit a lot of infrared light. Well, our own atmosphere is just the right temperature to emit an enormous amount of infrared light. It's hard to look through something that's glowing. Also, our atmosphere has water vapor in it. Water vapor is a very, very, very efficient absorber of infrared light. In fact, it is the most important greenhouse gas in our atmosphere. If there was no water vapor in our atmosphere, the Earth would be frozen. Now, we always hear about CO2. It's a much smaller trace gas, and it actually can push on the greenhouse gas trapping, greenhouse effect a lot more, but fundamentally, water vapor is the most important, the most abundant greenhouse gas, which is great for people, not so great for astronomy, because you can see this is transmission. You have a little bit of transmission at some infrared wavelengths, but almost none at these other wavelengths. So the atmosphere both absorbs the light thanks to the water vapor, and also is just warm enough so that it's emitting its own light. And this is what it would look like if we sort of translated the infrared to optical. In the visible and in infrared during daytime, you have a glowing sky. That's why we don't do optical astronomy during the day. At night, the sky looks like this. Well, if you're not in the middle of Los Angeles. But the sky should look like this. But the temperature difference between daytime and nighttime air is not that much. So it's still glowing with a lot of infrared. So, but if you can do infrared astronomy, what are you going to see? This is one of the few constellations that we can see with our own eyes from the middle of Los Angeles. If you can't find the blue lines, squint real hard, or drink a lot. The Greeks came up with this and they drank a lot of mead, so drink a lot and you'll see the blue lines, I guarantee it. But this is meant to outline the warrior Orion, and all we're seeing are the very hot things. So as I was saying, if you're very hot, any temperature emits light. The hotter you are, the shorter the wavelength of light it is that you emit. Our sun is hot enough that it emits mostly optical light. There's a lot of optical light that comes. Hotter stars emit even shorter wavelength light. They're bluer. Cooler stars are redder. And that's sort of this whole thing. Betelgeuse is actually a cooler star. It's expanded, so its surface temperature is lower. So if you look at it, even with your own eye, you'll see that it's a redder looking star than some of the other stars in the constellation. But this is what you see when you look in the infrared. This is very different than this, clearly. Why? Because this is surrounded by dust and gas, which is warm. It's not hot enough to emit optical light, but it's warm enough to emit infrared light. And so you can see that the universe looks very, very different in these different wavelengths. And that's why it's a big advantage to study the universe in multiple wavelengths. And the advantages that you get with infrared astronomy are fundamentally having to do with, again, primarily about temperature. That is, if you're dust surrounding a star, you're not going to be at the same temperature of the star. You're going to be cooler, but you can be emitting a lot of infrared, so you can see dust around the star. The dust itself can warm up and emit. There's a lot of chemicals which have chemistry that the spectrum is in the infrared. You can identify various, particularly organic compounds, can be identified in the infrared. But also, as the universe is expanding, things that are emitted in the optical or the ultraviolet, the expansion of the universe causes a Doppler shift, and that Doppler shift is taking shorter wavelength light into the infrared. So infrared astronomy is a very powerful tool. Even if we want to make it any simpler, sort of think of it this way. About 100 Kelvin, this is the stuff between stars. About 1,000 Kelvin is the stars, and about 10,000 is really hot stars. So stuff near stars is about 1,000, 10,000 is stars, and 100 is stuff in interstellar space between stars. So to take advantage of all of the different wavelengths, NASA had what was called the Great Observatories program, to put telescopes in space to observe at the wavelengths, particularly at the wavelengths that we couldn't get from the ground, but also even in the optical, the atmosphere is just waving around a lot and it makes the stars twinkle, very romantic, but not great for science. So that's what, the first one was the Hubble Space Telescope. Then they put up the Chandra X-ray Observatory. Fortunately, we don't get a lot of X-rays falling on us from space, but then that means you have to go into space to study things that are emitting X-rays. There's things that emit gamma rays. That was originally the Compton Gamma Ray Observatory, which was replaced by another one called the Fermi Gamma Ray Observatory. And then it was the Space Infrared Telescope Facility, which was renamed the Spitzer Space Telescope to do the infrared. And they have worked together incredibly well. All of the different colors here are different wavelengths. So the Chandra X-ray Observatory, this is a supernova remnant. This is the remnant of a star that exploded. All the blues and greens are X-ray emission, and you can see they're separated from the reds, which are the infrared emission. So it's like doing a diagnostic of what is this thing made of just based on the wavelengths that you're detecting from it. So Spitzer was built and launched in 2003. There are certain requirements. Yes?
All right, the previous slide,
sure.
Those different spectrums,
yeah.
are they all taken simultaneously?
Nearly simultaneously, not exactly simultaneously. But this supernova remnant...
Within a year or so, right?
Yeah, within a year. So this doesn't change that much. But if something is changing a lot in multiple wavelengths, you definitely want simultaneity. But not in this case. This doesn't change much. I mean, they've taken multiple images and they knew it didn't change much already. So the Spitzer Space Telescope was launched, and here are the difficulties you run into again in trying to do infrared astronomy. Is that if you're near the Earth, well, the Earth is warm, that's a problem. The sun is warm, that's a problem. So what you want to do is you want to have a telescope that's cold, because if your telescope is also warm, it's emitting its own infrared light. So it's a little bit like trying to do optical astronomy with a telescope that's made out of fluorescent light bulbs. Not a good idea. Your telescope should not be glowing in the wavelength that you're trying to study. So what you want to do is you want to make your telescope colder than the things that you're looking at. Doesn't mean that it doesn't emit light anymore, it's just that emitting it at a different wavelength than the stuff that you're studying. So what you do is you make it very, very cold. So first step is block out the sun. So there's the sun shield. The sun never hits the telescope. It will always have its back to the sun. Second, you can certainly be in Earth orbit, but it's ideal to not be in Earth orbit. And so we gave it a bit of a kick so that it's drifting away from the Earth, and it's called an Earth trailing orbit. So it got a greater distance from the Earth. So the Earth is warm, but it's far away. The sun is shining on the telescope. It's blocked by the shield. And then it was launched with liquid helium. Liquid helium is very cold. And with the evaporation of the liquid helium kept the instruments cold. And the evaporation of that kept the telescope cold. And this was kept cold at 5 degrees Kelvin. So that's how cold it was. That means it could basically detect anything that was warmer than 5 degrees. But if it was looking at something that was also emitting at 5 degrees, then it's emitting the same wavelengths of light that the telescope itself is emitting. So nothing that we could, but then again, there aren't that many things at 5 degrees in the universe. There's the cosmic microwave background, but that's a different telescope that you launch to study that. So it was launched, and due to orbital dynamics, it actually does a lot of these loops. Right now, it's very far away. It's actually 210 million kilometers away. It's now 1.4 astronomical units. away from the Earth. So the average distance from the Earth to the Sun is 1 astronomical unit. It's drifting away, so basically they're both doing the same 1-year orbit around the Sun, except it's taking Spitzer just a little bit longer and longer, so it's drifting away from the Earth, and now it's more than 1.4 astronomical units away from the Earth. And even though it was originally titled the Space Infrared Telescope Facility, usually telescopes are named after their launch. There are a few exceptions, obviously, and it was named after, there was a naming contest, and it was named after Lyman Spitzer Jr. He got his Ph.D. in astronomy and astrophysics from Princeton in 1939, and in particular, why it's so appropriate to have it named for Spitzer is that in 1946, it's 1 year after the end of World War II, the only thing rockets had been used for at that point was to basically bomb London. And this is 11 years before the Soviets launched Sputnik. And 12 years before the formation of NASA, he writes a scientific paper, not science fiction, but a scientific paper on the astronomical advantages of an extraterrestrial observatory. So in 1946, he's pushing for putting a telescope in space. And he's also considered to be the founder of the study of the interstellar medium, all the stuff between the stars and the stuff from which stars form. And so his area of study was very appropriate for the infrared. Starting in the 1960s, Spitzer put a great effort in trying to get the community to support a space-based telescope. In the 60s, the initial result was a telescope called Copernicus and worked in the UV. And then eventually, the result of all that lobbying was in 1977, Congress approved the Hubble Space Telescope, which launched in 1990, 44 years after he originally proposed a large telescope in space. But what's interesting is that he was still alive at that point and got Hubble Space Telescope data and worked on that. So his whole life's work actually came to fruition at a time where he could actually use it. So the reason we could actually do something like the Spitzer Space Telescope was advancement in technology. From the time of Herschel in 1800, it was very difficult to do any kind of infrared astronomy. In the 20th century, they developed infrared sensitive film, which again was not sensitive enough for the kinds of low levels of light that we get in astronomy. But then in the 60s, thanks mostly to the military for their heat-seeking missiles, there was electronic infrared detectors that were developed. This is an image of the center of our galaxy. It's not an image, actually. These are called strip charts. This was done with a single pixel. So what you would do is you would take the single pixel and march it across the sky. And so you'll see, depending on where you're pointing in the sky, there's less infrared light, there's more infrared light, and this is telling you sort of the distribution of infrared light that you're getting. Whoa, there's a big peak of infrared light here. And so that was when they were pointing at the center of our galaxy. Of course, years later, instead of having 1 pixel, when we finally got megapixel detectors, this is what our galaxy looks like. In the optical, you can't actually see the center of our galaxy because there's a dust lane there. But in the infrared, you could see it. The strip chart, though, was actually done at Mount Wilson Observatory. So when you're driving down the 210, look to the left after you pass the Rose Bowl, and you see all these antennae. Right next to the antenna is Mount Wilson Observatory, which is one of the most important observatories in the history of astronomy. Mostly optical astronomy, but that's where Hubble discovered the expansion of the universe. But the very first infrared telescope that took that survey was developed at Caltech, and it was put on Mount Wilson. And so the first infrared survey of the sky was also done at Mount Wilson. So with the invention of infrared sensitive detectors that have more than 1 pixel, we were able to make multiple instruments to put in Spitzer with horrible, horrible names. We have IRAC, the infrared array camera. We have the IRS, everybody's favorite government agency. Infrared spectrograph, that was built by Cornell. The IRAC was built by the Smithsonian Astrophysical Observatory. And then there's the MIBS, which just sounds like you have no idea what you're saying, but it's the multi-band imager and photometer for Spitzer, and that was built at the University of Arizona. And notice how small these instruments are. These aren't giant, giant telescopes, giant cameras. These are about this big. Because anytime you send anything into space, mass is what drives the cost. So what did we see? Well, this is an optical image of what's called the elephant trunk nebula. Hopefully you can see that. This is the elephant's head, the mouth, the eye, and the elephant trunk. It's actually a star-forming region where a lot of young stars are forming, but if you look at it in infrared, you can start penetrating through all of that dust to see the stars forming. So what I'm going to do now is do a little bit of a review of all of the things that we were able to study with Spitzer, starting from literally in our own astronomical backyard, starting with asteroids, going all the way to the farthest reaches of the universe. So one of the critical things that Spitzer studies is asteroids. It's not that it's not discovering asteroids that's the important thing. The important thing about when you're studying the infrared is what are the masses of these asteroids. In the optical, what you're getting is the reflected light from the surface. But the reflected light from the surface, all it's telling you is the materials that are on the surface. For example, if it's covered in ice, it will be very reflective. If it's not covered in ice, if it's covered mostly in charcoal level dust, it's not going to reflect a lot of light. But that's not telling you what the mass of the source is. But based on different ways of observing in the infrared, you can actually tell what the mass of these objects are. Because they absorb sunlight, they warm up, and they start emitting infrared light. And so the level of infrared light emission then can be measured against the change in the orbit, because the amount of infrared light that they're emitting acts like a little thruster and changes their orbit. It's hard to believe that just emitting light will change an orbit that much, but then it changes the orbit. So the change in the orbit, we know what's the force on the asteroid, so something's pushing on it. We've measured the infrared light that's coming off of it, and then we look at how much it changes, and that depends on the mass of the asteroid. So if it's a less massive asteroid, even though it could be very big, but it could be very low density, so the infrared light that comes off of it, so it's pushing on it. If it's low mass, its orbit will change a lot. The infrared light that's coming from it, if it's a high mass one, it'll change the orbit very low. Yes?
Isn't the infrared coming off of it kind of omnidirectional?
No, that's the thing. It's sort of omnidirectional, but not quite. It's mostly coming from the sun-facing side, because as it turns around, it cools off fairly quickly. So it's not obviously it's not just in the direction of the sun, but if you model, you can actually model it based on the rotation of the asteroid. But it cools off very quickly, so it's not emitting a lot of light to the dark side of it. But that's the thing. You have to actually get the full rotation. You have to know what it's doing. It's not just sitting there. That'd be the ideal case to do it, but yeah, in this case, you do need to know the rotation of it. But the dark sides, these things cool off very quickly. So anyway, Spitzer has measured over 100 asteroids for their masses, and this is really important because we really need to know, especially for the Earth-crossing ones, how dangerous they are. Because if it's a very low-density asteroid, it really doesn't present that much of a threat. Low-density asteroids will most likely explode high in the atmosphere. They may do some damage, but they're not dinosaur killers. But if it's a very high-density, iron-level kind of, mostly iron asteroid, that's when you have to worry. That's the kind of damage that can really destroy an entire city or half of a continent. So we want to be able to know which ones are the bigger threats. Which ironically, by the way, you never blow up an asteroid if it's going to hit the Earth. You use the same idea, except instead of doing it with the infrared, you do it with mirrors. If it's long enough away, you put mirrors in the right positions on the asteroid, which means that it effectively acts like a little thruster because it's bouncing the sunlight off of it. And if you do it in the correct direction, it'll just tilt it just off enough so that it doesn't hit the Earth. Only if you detect it early enough. It can't be like a few weeks from now. If it's going to hit us 10, 20 years from now, putting the mirror in the right location, very cheap, no chance of shrapnel hitting us. Then there are comets. Comets, most of it, this is what we're used to, lots of gas, reflects a lot of light, but you can't see what's going on to the comet core itself, and the comet itself, where it's emitting, where a lot of dust, as you can see, is coming off of it. But Spitzer could see through all of that and see how the comets changed as they approached the sun. The other important thing was we could do the chemistry of the comets by taking a spectrum. And during the time that Spitzer flew, there was another mission, also from JPL, called Deep Impact. This was the brilliant idea that maybe if you want to study something, you should crush it. That's the way you study stuff. You break them, which is mostly what the particle physicists do. But this is the same idea as, I want to study how a Rolex watch works. Let's do this. Oh, oh, look, and gears and everything. But that's what we did. We actually took a piece of copper, slammed it into the comet, and basically got what's inside. Because usually from the comet, we're only getting what's on the surface. But here, this is from the interior of the comet. So it's much more pristine, and it has a record of what it was made out of originally. And so then Spitzer could do a good spectrum. They could do spectra from the ground, but of course, a lot of the organics you saw, you can see it only in the infrared. This is one of my favorite discoveries that Spitzer made. The biggest ring of Saturn, and we've known about Saturn for a long time. Galileo was the first to look at Saturn with a telescope. He saw the ring then, and from the point, well, he thought it had ears, but his telescope wasn't that good. But after a little while, another astronomer named Cassini discovered that, you know, this must be a ring around Saturn. And for several hundred years, we've known about the ring of Saturn. And then we've had bigger telescopes and better telescopes looking at it, and the Hubble Space Telescope looking at it, and we missed the biggest ring it had entirely. Why? Because it was very, very thin. There's this very thin dust ring that's out in a very, very large orbit. And to give you a sense of how big that is, to scale, this is again an artist's conception, that's what Saturn would look like. That's its largest ring. But you could see it in an infrared because the dust is warm and it's actually emitting a lot of light. Well, that's emitted light versus scattered light, because it's so thin, it was very hard to detect. But Spitzer was able to detect it. The next level that I'm going to talk about are, the next set of discoveries have to do with star formation. There were a lot of theories of star formation before Spitzer flew, but there was a relatively little amount of observational evidence. The difficulty with the observational evidence is star formation takes place inside these dust clouds, and gas and dust clouds, and the dust is obviously blocking the optical and the ultraviolet in the wavelengths that we usually have looked at. We could look at some infrared light from the ground, but Spitzer was really going to give us this big advantage of looking at the star formation. So basically, what you have a sense of a star formation is you have a dark cloud. There's some portion of it that becomes higher density and sort of starts collapsing. Within that, you start getting some level of fusion, which starts generating energy, so it's now pushing against the gravitational collapse. And usually some sort of a disk forms. In that disk, you will, we think, eventually get planets, and within this core part is where the star has formed, and it's generating energy, and that the light that it generates basically clears out the rest of that gas and dust, and so you get a solar system, what we're used to. But this was very hard to observe because most of the time we couldn't see it. But here's a very interesting star formation region. You can see the gas and dust here, but right here, in some of the areas where it's been pushed in, you can see this collapse happening. A whole bunch of stars are forming here. And this isn't just your imagination that there seems to be a wind blowing. There's actually a large number of stars off the image here that are pushing on this, and that shoving and compression is causing all these stars to form within the gas and dust cloud. This is an image called the Pillars of Creation. It was taken by the Hubble Space Telescope. We don't have the same resolution as the Hubble Space Telescope, but we cover a much wider area. And so this is the sort of comparison to scale. Here's another star-forming region. There's a star in here that's actually sort of cleared out the region and caused shock waves around these regions to start forming young stars. To be more specific, looking at that region, you can see this is, again, the Pillars of Creation. And the optical, it's very hard to see within these dust clouds. But for example, for this dust cloud, it's so clear now there's a young star forming at the tip, hidden inside that dust. Now, of course, star formation is interesting, but what we're really interested in are planets. Now, here's an artist's conception of how you can try and find planets using Spitzer data when you don't have the resolution to actually see the planet. But if a planet is forming from this disk of dust from which the star has formed, the planet itself is tiny, but as it clears out its region, it's going to leave a hole. So it's a secondary evidence. It's circumstantial evidence that there's a planet there because the dust doesn't go all the way to the star. A region has been cleared out. Or if there's multiple planets, you would get something like this. Now, the disk, and as the planets are forming, again, the planets are tiny, but basically by clearing out region, you can see that there are planets forming there. Okay, also, does this remind anybody of anything? Anyone? What did this look like halfway through? Saturn, exactly. Now, it's not exactly the same mechanism as what's happening in Saturn, but that was one of the discoveries that was made by the Voyager mission, is that a lot of these rings, although it's not that they're moons that have formed in there, but they're shepherd moons. So even though you don't see the fact that there are moons here, the fact that there are these specific gaps are in fact associated with moons. So you don't see the moon itself, but you see the evidence of the moon. And this is what we were going to do with Spitzer, is we don't see the planet itself, but we want to see the evidence for that planet. How do you see that? Well, a star emits a certain amount of light. A star plus the dust around it will emit the starlight plus an additional amount of light that comes from the disk. But if the disk has been cleared, then you're going to have a gap. And this is actual data. We have seen, this is the stellar light and these gaps that are formed around these stars. So that's our first good evidence that planets are forming there. There's another star which is actually very nearby. It's very young, and it's been known. You can see anytime that if a star has a name, it means it's bright enough to be seen by eye. Anytime there's an al in there, it was the Arabs who were cataloging it as Famalhat. It's usually called Famalhat. And what it was when we looked at it in the infrared, in the cooler dust, we could see literally there's a hole in the center of that disk. Now, it's not quite the same scale as our solar system. It's about 370 times the scale from the Earth to the Sun. But still, it's a way of finding planets around other stars, particularly young stars that are just forming and they have a disk and the disk is being cleared out by planets. The other thing we do is we start looking at these what are called protoplanetary disks, and to look for the things that we think are the precursors of life. Anything that is an organic compound, carbon and hydrogen. And we've detected a large amount, well, water we think is important, and water is ubiquitous. You see water almost everywhere in the universe. But we've also seen acetylene, hydrogen cyanide, so there's various different things that once you put them together in the right way, you can actually have them be the starting blocks of life. But what about older stars? Here's another animation. What happens with older stars, and why would we care about older stars? Well, what we think happens in older stars is they have asteroid belts, or if they do have asteroid belts, you will have collisions between those big rocks, and they would create an enormous amount of dust. And here's a sort of a sped up version. Assuming you have all of these collisions that are happening, they would create these dust trails. So it's almost the reverse of what we had before. Before we had a lot of dust and you had these gaps being carved into them. Here we have basically, it's mostly clear, but if you have bits of rocky things, they can collide and they can create these dust trails. Very much like the largest ring of Saturn, then you can actually see these much more easily in the infrared. And again, this is an artist's concept of this. But we started looking at older stars to see how often they had these kinds of dust disks around them. Why do we care? Well, rocky planets are the smallest planets that there are. Basically looking at our own solar system, Mercury, Venus, Earth, Mars, very small. So it's not going to be easy to ever really see these kinds of planets. There's other methods that I'll tell you in a little bit. But fundamentally, what we're looking for is evidence that there's rocky stuff there. Well, what's the evidence for our solar system? Well, it's Earth, Mars, Venus, and Mercury don't leave much of an evidence. But we do have the asteroid belt, a planet that didn't actually form, but there are bits and pieces of it, and they basically collide, they create dust trails, and so it tells you that, oh, at least some form of a rocky planet or remnant is still there. And it emits a lot of infrared light. And so we can look at what happens for younger stars when they have a lot of dust disk, and then eventually, mostly it clears out. A lot of them don't seem to have these disks. This is a little bit of a controversial thing because everybody, the numbers range from 20% to 60%, that's a big range, have dusty disks. But if the key question is, really trying to get that number more accurate, but the main idea here is if there are things like rocky, asteroids in these other solar systems, that tells us a lot of things. That is, one of the things is our moon formed from a giant collision between planetesimals. Our moon, you wouldn't think in and of itself is very important, but as far as we know, the moon has played two very important roles in the history of life on Earth. One is it's a blocker. It seems to block a lot of things that may have hit the Earth and destroyed the Earth, particularly because it's very big. The other one is that it causes tides, and a lot of the early life that we think formed in tidal pools. That means it doesn't, it allows these little areas of water to form and hold together because of the tides coming in and out. And so if we're interested in having Earth-like planets in other solar systems, finding those kinds of planets, then we want to know what's the probability that those kind of planets could form, Earth-like planets could form. Well, for that we need rocky stuff, and we're trying to figure out how many stars like our sun have a lot of these kinds of debris disks. That's still a little bit up in the air, but at least 20% have it, maybe up to 60%. Now, finally, this was something entirely unexpected for Spitzer. Until 1995, we knew of 9 planets in the universe. By universe, I mean the entirety of space. Mostly because those were the planets we knew in our own solar system. Now, we demoted Pluto, so it's 8, but in 1995 it was 9. So what's the question there is that, how often do other stars have planets? So there are all these different techniques that people were trying to find planets around other stars. And they started finding planets around other stars. First a few, then more and more and more. And then finally, they came up with this technique, which is called the eclipse technique, where a planet around another star passes in front of it and just blocks out a tiny bit of the light of that star. Now, Spitzer was never designed to find these planets. In fact, that's not its job. All these other techniques, particularly this eclipse technique, started finding planets. But what Spitzer could do was follow them up, get information about these planets, other than the fact that they existed. And these are not Earth-like planets. They're more like big Jupiters right next to the sun. And this is not imaging of the planet by itself. These are our observations of already known planets, of hot Jupiters, and we get the light of the star plus the planet. Let me give you the animation here. So this is what happens. You have a star, it's emitting a lot of light. The planet is warm, is also emitting a lot of light. So you have the combined light of the star plus the planet. As soon as the planet goes behind the star, now you don't have this planet's light being added until it comes out. So you get this dip. Now once the planet passes in front of the star, which is usually the way they're discovered, this is in optical light, what you see is the planet blocks the star's light. And that's usually how they're discovered in the eclipse technique. There are other techniques as well. And so that's a 0.5% dip. But Spitzer was built so well that its cameras were able to pick up these 0.5% dip and start studying these planets, because what can we tell based on the amount of infrared light that's coming off? We can tell the temperatures of these planets. Remember, the hotter something is, the more it emits, and the wavelengths of light that is emitting will get shorter and shorter. So the ratio of the infrared light that was coming from one wavelength versus another can tell you the temperature of the planet. And in the case of the first 2 that we were observing, they were at least 1,000 Kelvin, about 727 degrees Celsius or 1,314 degrees Fahrenheit. So they're hot Jupiters. And so we've been following these guys up to study more and more about them. There was one, in fact, where it didn't even actually eclipse its star. But what it was doing is it was orbiting, so it would show us the hot side, more infrared light, then the cool side, less infrared light. And then as it's going around, it would give us more infrared light as the hot side came into view. So we could actually follow it in its orbit based on the amount of infrared light that it was giving us. And in this way, we could actually understand what was going on in its atmosphere. Because if its atmosphere redistributed its heat from the day side to the night side entirely equally, that means the day side and the night side have the exact same temperature, then you wouldn't get this effect. So what this is saying is the day side and the night side temperatures are significant. They have to be different, but what's interesting is they're not that different. It's 970 degrees K on one side and 1200, it's almost a 300 degree difference, but not enough. And so what that says is that the heat has to be redistributed fairly quickly across the planet. So the side that's facing its star gets heated up, but then that heat has to go to the cool side to warm it up. To do that, you need about 6,000 mile per hour winds to redistribute the temperature to that level. Now, let me repeat this one more time. Yeah, I just said 6,000 mile per hour winds on another planet, but that's a weather report. That's what you get when you turn on the evening news here about what kind of winds, what the temperature is going to be, what the wind speed is going to be. We've now done a temperature and wind speed on another planet by using the infrared light. And people have been able to model sort of the kinds of winds that you could have that. We finally actually also did the first spectrum of planets outside our solar system. And there were two different ones that we observed, but I'm going to show you the results for one. Again, same approach. This is an eclipsing planet. So planet plus star, it gives you the star spectrum and the planet spectrum simultaneously. Again, we don't resolve these two. It's one blob. So, but then, once the planet goes behind a star, you're getting the star spectrum only. Literally subtract the two, then what you're left with is the spectrum of the planet. So now, you can actually get a sense of what the planet has, and in this particular planet, it actually had a fair bit of water vapor. These are the water vapor absorption lines. And we were able to do about 20 exoplanets like this, to do the chemistry of their atmospheres. So going away from stars in our own galaxy, we can talk a little bit about other galaxies, which is part of a great deal of what I work on. This is what a galaxy sort of like ours looks like. About 100 billion stars, except this one has another galaxy that it's cannibalizing. It's a process called galactic cannibalism. But anyway, in the infrared, it looks very different. The dust lanes, instead of being dark, are warm, and so we can see them glowing. And again, the colors here are representative colors. People often call these false color images. There's nothing false about them. What we're doing is assigning a color to a wavelength. And we try to be consistent in the approach that we do. For our own eyes, the shorter wavelengths correspond to blue light, the middle wavelengths correspond to green light, and the longer wavelengths correspond to red light. So anytime we have infrared light, that's also the same. So the blue light here is not the blue light that our eyes see, but this is shorter wavelength light than the red light here in the infrared. We're never going to see in the infrared, so we can't, there's no way of doing that. So we're trying to represent the wavelengths, the image that we would see if we had infrared sensitive eyes in this way. Shorter wavelength is, again, assigned to bluer colors, and longer wavelengths are assigned to redder colors. Here is actually a fairly famous galaxy called the Sombrero Galaxy. We can sort of see it in the infrared. The infrared actually gives you a slightly different. Anybody ever played with an arrow bee? Anybody remember the arrow bee? Ring you would toss around. It's a frisbee with a hole in it. And it looks more like that. Just Google it. And then one of the advantages of Spitzer was that we could do these very large surveys of the sky. It's not an all-sky survey, but we did huge chunks of the sky. And no, we're not looking right next to the moon. This is just to give you a sense of scale. So what's happening here is this is just one of those surveys. We did this huge survey, much larger than a full moon. And what we're doing is we're trying to look for things which are unusual. But the problem, of course, is how do you find anything when you have a survey like this and all of these sources that are in there? Well, one of the advantages is that when you have different wavelengths that you're looking at and the universe is expanding because of the Doppler shift, what ends up happening is the peak emission of whatever you're looking at is now shifting to the red. That is, it's changing. and changing to a longer wavelength. And in particular, so this is sort of optical and near IR, which is what the Hubble Space Telescope mostly works in, and then this is the Spitzer infrared bands. And so what you can see is that something gets Doppler shifted, so this is the emission that it has. It peaks around 1 micron, but as it gets redshifted, it gets into the Spitzer wave bands. So what you can do is you can say, okay, here is an image of the sky at 1 micron and shorter, and it doesn't tell you anything. But if you're looking for galaxies, and particularly clusters of galaxies, and clusters of galaxies that are far away, then these should be redshifted, and so their peak of emission should have moved into the Spitzer bands. And so if you do that, in fact, that's exactly what happens. So here's an image, here's the Spitzer image, here's an optical image. It's not clear that any of these sources are associated with each other, but in the Spitzer image, it's really obvious. The peak of the emission has moved into the wavelength that our camera is sensitive to, so you can see that these guys are all associated with each other. So you've discovered an entire cluster of galaxies. And the clusters of galaxies are basically the building blocks of the universe. So you can do a nice Where's Waldo game here and look for these sort of groupings of sources which have similar brightness in the infrared wavelengths that Spitzer is looking at. And then you can go back and do a spectrum to check to see that that all of those sources are in fact the same. So Z is a measure of redshift, and so this is a galaxy cluster at a redshift of 1.4. Again, previously unknown. And this was the difference. These are the numbers of, so the higher the redshift, the further these objects are, the faster they're receding from us. We knew a lot of nearby ones, not very many far ones, but as soon as Spitzer came along, we had a huge increase in the number of clusters. And then my favorite thing, supermassive black holes at the centers of galaxies. The problem when you're trying to study a giant black hole, well, black holes in themselves don't emit any light, but as material falls into them, the material heats up and you can study that stuff that's going into the black hole and help you study the black hole as well as the material that's falling into it. Unfortunately, the centers of galaxies tend to be dusty, and so you can't see, except if you look at an infrared, the hot stuff is shining brightly, and so you can penetrate the dust and detect a lot of the accretion onto the black holes. It's a little bit of an unfair image, but I'll use it anyway. So here's a Hubble image. Nothing seems to be there, but there's clearly something there in the Spitzer image. Also X-rays. X-rays we know penetrate. You know, that's why we use them in the dentist's office or the doctor's office. So they can also penetrate the dust, and we can detect these accreting supermassive black holes. And why are they important? Well, it seems like every big galaxy has a big black hole at the center of it. It's not clear whether it's a little bit of a chicken and egg. Do you need a black hole to form a galaxy around it, or do you get a big galaxy around it and then which forms a black hole at its center? But studying black holes is very difficult because they don't emit anything, but fundamentally it's one of those things where what we're going to do is study them using the secondary method, studying them through their accretion, even though the black hole isn't emitting any light. So again, you can do a search for those kinds of the emission that's coming off of the black hole, and then in this huge survey we could then pick out huge numbers of these active galaxies and go back and confirm that they're in fact active galaxies, and we picked up some of the most distant objects in the universe with this technique. And finally, what you want is one of the bigger advantages, and again, combining the great observatories. You have the Hubble Space Telescope and the Spitzer Space Telescope, and what we think is the earliest galaxies, this is sort of the light that they're going to be putting out. They're not putting out, they're putting out a fair bit of light here, and this isn't even originally in the infrared. This is actually in the optical, which has now been shifted into the infrared. And then here we have basically a break in the spectrum. So if you look at it in the Hubble, you have a little bit of light. If you look at it in Spitzer, and it has a lot more light. You're actually picking up something that's very, very, very early in a galaxy. And this particular one is 13 billion light years away. This is when the universe was only 15% of its present size, only 7% of its current age. And so Science News had a sort of amusing approach to describing this particular galaxy. It was a much more advanced and much more mature galaxy to find so early in the universe. And so their description of it was it's a little bit like looking at the nursery, little baby ones, and then you have this galaxy which is a little bit looking a lot older. He's got glasses. His name is Herman. But that was an interesting thing, is we've been able to pick up that some galaxies clearly evolved very fast and became fairly mature galaxies without much other things going on very early on. So that's an interesting, they're very rare, these kinds of galaxies. Most of the galaxies we see in the early universe are more baby galaxies. They have a lot of active star formation. They're very typical in what we would expect to see, but Herman was not. After about 5.5 years, the liquid helium for Spitzer ran out. And so we couldn't stay at 5 degrees Kelvin, so we started warming up. So we warmed up all the way up to 30 degrees Kelvin. And that's now called the warm mission. So we have an extended mission. Most of our instruments don't work, but two of the channels of our infrared cameras still work. So this is our sense of the warm mission. If you think 30 degrees Kelvin requires a nice palm tree and a nice drink. So now we're operating at a higher temperature, but still this has given us advantages that of things that we couldn't do before. In particular, because we're now switching between all the instruments, we have this one camera that we're working with. We can look at the same location in the sky and just look for things that are varying. And so these are young stars, and variability in young stars is really important. It gives us a good sense of how they form also. We can look for these very, very, very distant galaxies that are very young. And this is a good way of finding it. Spitzer is very useful for finding that. And so you can spend a lot of time looking for those. And then finally, the other aspects of Spitzer are actually gone beyond just the scientific community. There is, this is called Astronomy Today. Chasen and Macmillan is one of the standard astronomy texts. They use one of the Spitzer images for its cover. Of course, you're nothing if you don't make it in Hollywood. This is a movie called Stranger Than Fiction. The image behind them is a Spitzer image that they printed out and used. We're very happy about that. And basically, this is what Spitzer is doing and what it's going to be dealing with, and it's setting up the stage for the key aspects of the fundamental questions that NASA wants to study. That is, where do we come from? Are we alone? And where are we going? And it's addressed some key aspects of this and has set up sort of what is essentially the follow-up to Spitzer, and not, although oftentimes it's called the follow-up to the Hubble Space Telescope, is the James Webb Space Telescope. But the James Webb Space Telescope operates very little in the optical wavelengths. It's fundamentally operating mostly in the wavelengths that Spitzer works in the infrared. And so a lot of the discoveries that have been made by Spitzer are all precursors now for this incredible new telescope that's going to be coming, hopefully launched in 2018. But fundamentally, that one will also be trying to address all of these questions. Where do we come from? Are we alone? Where are we going? And your taxpayer dollars have paid for all of this, and all of this stuff is online. So I really encourage you to go and try and find out about all of the different aspects of these questions that Spitzer and the other great observatories and all of the astronomy that NASA supports have tried to answer. Also, if you're interested in just in JPL in general, October 10th and 11th is JPL's open house, 9 a.m. to 4 p.m. Anybody can come in, there's no restriction. There's a lot of displays that will be put on by the different divisions, not just the astrophysics division, but the divisions that do Mars and study Mars, and the rovers, the planetary sciences divisions that people who study Saturn, and all of those things will be on display. So I encourage you, if you haven't been to JPL, come to JPL during open house. I encourage you to come early, partly because it gets really hot, and partly because as it gets more and more crowded, the less and less you can see. So it starts at 9 o'clock in the morning. You can also just do a JPL open house search, and it'll come up and you'll see more details and maps and where to park. And that's it. Thank you very much.
Thank you very much for this informative and interesting. Any questions? Any questions? Yes, please.
I can ask you offline. I see you very.
No, I know you were. Yeah.
What's the end of life on Spitzer?
End of life is a race between budget and physics. So
what's the physical limitation?
the physical limitation are that get a picture of the spacecraft up so that I can actually. So the way Spitzer communicates with the Earth is there's a radio dish at the bottom of the spacecraft. So it basically has to turn the spacecraft so its butt is facing the Earth so that it can communicate with the Earth. So the limitation is, so if this is Spitzer and this is its communication disk and this is Earth. So if you're over here, the shield protects you from the sun and you can talk to the Earth without a problem. If you're here, shield protects you from the sun and you can still talk to the Earth without a problem. By the time you're getting around here, which is where we're getting to, if you want to talk to the Earth, now you're seeing the sun. The sun is shining on the bottom of the telescope, warming it up. So that's the physics limitation fundamentally, that as we're orbiting here, it's going to start getting sunshine on the telescope and you just can't have that, and it'll warm up too much and we won't be able to use it the way we're using it. That should be, nobody knows exactly when, but around 2018 or so.
Can you wait until it comes around?
Well, we could, but the reality of it is that it'll take a long time, so it's not clear that it would still keep functioning. And that's actually one of the problems, that's the money problem, is that because our fundamental main mission with the liquid helium was finished, now we're in the extended mission phase. An extended mission has to be renewed every 2 years. So we basically have gotten all the renewals that we think we're going to get. There's one more that we might get and that we're applying for. This is called what's called a senior review. NASA always reviews its missions, and those that have these extended missions, then what they do is they give you a 2-year extension. And so I think basically we might get one more 2-year extension up to the point where we would have to basically expose the telescope to the sun. So fundamentally, that's the physical limitation. Whether we get renewed until we reach that physical limitation is not clear. Our budgets are very tight. But if we do, it's unlikely that we would go after that, because you would have to basically put the spacecraft in hibernation, wait for many, many years, hope nothing breaks, and then pick it up on the other side. By that point, although Spitzer is unique in many ways, and in some ways it will definitely be surpassed by the James Webb Space Telescope, it would be nice to have an equivalent many years from now, but it's unlikely that we would ever resurrect it once it comes out the other side. And it would be many, many, many years from now. There's just very little chance that it would keep functioning.
How fast do you get the data from?
A lot slower now. The farther you go, the lower your downlink rate becomes. I think right now we're at a few hundred kilobits per second. So it's not even, we're not at the data rates. I think we might actually still be going to 1 megabit per second is the downlink rate. But that involves the biggest radio dishes that we have to communicate with it. And those are what are called the 70-meter antennas. JPL operates this for what's called the Deep Space Network for NASA. And we have these giant dishes and some smaller dishes in California, Spain, and Australia. So that as the Earth is turning, and if I'm going to try and get downlink from you, I always have a dish that's facing you as the Earth turns. So you need these three, and usually two stations at one time can actually look at you, so that there's a handoff between them, where if one of them fails, you can still do a lot of it with one. But the reality of it is that there's one 70-meter dish at each location. And so many missions now require a 70-meter dish downlink that it's becoming very hard to do this, basically bargaining between missions about how long they can get it and how long they can do the downlink. Spitzer absolutely needs the 70-meter dish, so we get the time. But then Mars has a lot of downlink that comes down, so we usually have to compete with them. Now, the Pluto mission that went by, there was a lot of downlink that needed to be done, and they could only do it with a 70-meter dish as well, and they're not even close to a megabit per second. I think they're slower than dial-up. That's like something like 25 kilobits per second, because they're so far away. So it's always a battle to do the downlinks, but we're at about a megabit per second, I think, at this point. We were higher when we were closer to the Earth, and we could use smaller dishes, and we didn't have to compete as much, so we could have a lot more time. So now we have less time at a lower rate, so we have to be very careful on how much data we're getting down. Yes?
After studying all these bits and pieces of galaxies in the universe, the question that you put on the board was, where are they coming from? What are you looking for? Or what may be human or scientists be able to find that you may say, oh, aha, now I know where we are coming from? What are you doing?
It's basically the questions of, what were the things that were necessary to come together to have a place like the Earth, and then on that place like the Earth, then you would have life evolving. So these are the questions that we want. The earlier ones were, and we've just finally, after a very long time, started answering this question, is how often do planets form around stars? Spitzer was a part of that, but particularly there was another mission called the Kepler mission, which was really looking for the frequency of planets around other stars, which seems to be very common. Now, you might think that's an obvious answer, but we didn't have observational evidence for that. But the reality is that planets are very common. Great. First statistic. Now, the next question is, how often do you have planets like the Earth, rocky planets? And that's what people are working on now. Then the question after that is, once you have rocky planets, how often do they happen to be in places where you would have liquid water? Now, it doesn't mean that all life needs liquid water. It's all life that we know of needs liquid water. So again, we're looking for things that we can recognize. Who knows if we would recognize another life form that doesn't use liquid water? That's fine, but we may not recognize it. But for the things that we recognize is we need liquid water. So how many of them are at the right distance from their sun? Not too hot, not too cold. And then the next step after that is what's going on there? Is there any kind of activity that gives us a clue? We're not going to be instantly getting, none of our telescopes are going to be powerful enough to take an image of the planet anytime soon, but we can study them with these techniques and get a spectrum and see whether they have water vapor in their atmosphere. Do they have ozone in their atmosphere? Ozone does not occur naturally, in the sense that if you have all the chemicals in the universe, you just throw them at different temperatures and different densities, you're not going to get ozone. What you need to make ozone, or various other, or O2, is the thing that makes life possible, is plants. So that's the next step to look for, is something that creates things that are not chemically found in, without some form of an input by life. And then after that, hopefully then we get something that has a sense that there's some technological civilization out there. So that's the main thing, is are we alone? Are we the only one? It's not likely, but we want to find evidence of other life around, and also just, where has that life been? And if you want to look into more detail into this, this is all part of something called the Drake equation. And it's not really an equation in the sense that we're used to, but basically these are all the statistical probabilities that come together that you think, when you put them together, will give you the probability of how many life-bearing planets there are in our galaxy. So that's basically what we're looking for. All of these different steps. What comes together, and what's the evidence that the kinds of things that we think will give us life are out there? The planets, the chemistry, and eventually some sort of technology. So that's what we're looking for.
I think I missed this. Is Spitzer revolving around the Earth as it's going?
No, it's Earth trailing. It's Earth trailing.
So it's always behind.
It's behind the Earth, and it's trailing more and more and more.
Not orbiting the Earth.
No, it does not orbit the Earth. It orbits the Sun in the same orbital path as the Earth, just a little bit slower, so that it's basically the gap between the Earth and Spitzer is increasing over time.
So the Earth can never grab it and bring it into its...
No, what will happen is eventually at some point Spitzer will slow down enough so that the Earth will catch up on the other side.
I see.
And that's about, I think, 60 years was one of the orbital planners told me, yeah. Yes?
If luck was smiling at you and your carte blanche bank account, is there a plan for Spitzer 2 possible?
No. James Webb is a little bit Spitzer 2, not quite. Spitzer was really designed for what's called pointed observations, that you still point at certain things, but we also could do very large surveys. Look at huge pieces of sky or look at a huge number of targets. James Webb, although it works at the same wavelengths as Spitzer, is a lot more sensitive than Spitzer, it has better resolution than Spitzer, but it looks at tiny pieces of sky, particularly compared to Spitzer. So James Webb is, going to be doing a lot of follow-up we observed with Spitzer, but the ideal would be then to have a Spitzer follow-up with much better technology, because again, we're flying 1990s technology here.
Yeah, that's really old now.
And particularly, and first of all, everybody knows in your computers, you're not going to be booting up your Windows 95 on anything. because it's CPU and everything. You just forget it. But that's essentially what we're doing. Is although our computers were better, that we had, but the technology for the detectors are, think about what the CCD cameras were like for your earlier cell phones. So imagine that that's the technology that you're flying versus what you have in the latest iPhone. So what we would like, I think, again, this is much, much later.
But by the same token, I'm thinking cost of technology having decreased tremendously. I remember buying my first Motorola brick phone for $600. Is there a cost feasibility to produce?
Here's the interesting thing about anything that goes into space. This whole thing could be made out of regular bricks, and it would cost about the same. Because the cost of going into space isn't the technology that you're sending there, the cost is the mass that you're sending out. So obviously with newer technology, the mass is dropping, so that helps us on that side. But what we really need is to change the cost structure of what we're putting up in space. So this has to do with the rocket side of the equation. SpaceX here in El Segundo is really working on that. There are these private companies and there are various different kinds of things that are working on trying to make it so that it's a lot cheaper to put largish kinds of things in space. If that's achieved, then yes, things become very, very different at that point. Because the technology has made things lighter, that's, you gain on that, and then the rockets are cheaper, and so you put them together, and then suddenly, this was, actually, an interesting story. This was a $2.1 billion mission, at which point it was canceled. It was too expensive. But because they came up with very clever technological solutions, one of them was this Earth trailing orbit. Nobody had ever done that before. One of them was basically what's called the warm mission. Usually you put your telescope inside the liquid helium. Here, the liquid helium is at the bottom, evaporating and cooling the telescope. The only reason you can do that is because you're not around the Earth. So the Earth trailing orbit and what's called the warm launch, so various technological advantages, took it from a $2 billion mission to a $700 million mission. So we basically did it, made a change of a factor of 3. So in and of itself, Spitzer was already getting an advantage of the technological changes, and our sensitivity was much higher because the detectors that were being developed were much better. But compared to the kinds of infrared detectors that exist today, this is ancient technology that's flying.
Can I ask you what size is actually been?
Yeah, let me see if I can have another picture.
Just roughly.
It's about 3 people high, I think, total. Maybe not even that. Where is it? Okay. So this section, where this person is standing next to, this is basically a little bit smaller than the full circumference of the. And so if this guy stands up and another guy stands up on his shoulders, they're most of the way to the top of the telescope. So yeah, it's not a very big telescope. The mirror itself is 85 centimeters. It's not even a meter big, so it's about that big. And that's, again, all the advantage of both being very cold so that you can really detect most of the infrared photons. So that's how you get a trade-off when you're doing infrared astronomy. Most astronomy is like, oh, bigger mirror is better, bigger, 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 which is true, but then if it's a bigger mirror, it's harder to cool it down.
Thank you.
Yeah.
What's the sensor resolution on Spitzer and then compare that to James Webb?
Oh, yeah, so the sensor we flew, these are 256 by 256 detectors. And James Webb is megapixel, it's 1K by 1K. Maybe even bigger. I think they might even have 2K by 2K. But I think at least it's 1K by 1K. So at least 4 times in each time, so 16 times more pixels already.
Can you say it's even narrower with you?
Well, yeah, when you get a bigger mirror, this is 85 centimeters, so less than a mirror. James Webb has this unfolding mirror, and the unfolding mirror gives you 6.5 meters. So that's huge. Now, it doesn't operate at the extreme wavelengths that Spitzer did because it can't cool down the mirror that much. But for the wavelengths that it overlaps, so Spitzer went from 3.5 microns to 160 microns. James Webb goes from 0.6 microns to 28 microns. But the overlap between 3.5 and 28 microns, I mean, that's a huge resolution increase over 85 centimeters. Yes?
Spitzer can detect hurricane or earthquake.
Not on the Earth. I mean, but what's interesting is that one of the moons of Jupiter has actually volcanoes on it. And so it has been observing for those kinds of volcanoes on these other moons of other planets. So, and of course, the one thing that we've been detecting is these, the change in the atmospheres of the planets, and the further planets certainly have hurricanes on them, so it's not hurricanes on Earth, but hurricanes on our own solar system planets. Spitzer could monitor them, and hurricanes are fundamentally a difference in temperature. So it was able to, do that kind of work. I think this is planetary work, so it's a little bit out of my experience.